This is the development section of the design coursework. Unlike the planning section, this is very different to the assembly coursework. It is also the longest and the most tedious section. So get going on it early, crack on with it, and get it done. It is a case of repeating. So this is a section where you are repeating things many, many, many times, and it's easy to get bored and make stupid mistakes. So make sure that you're very careful. So this is the bit where you are writing a specification, alternatives, circuit diagrams, test procedures, test results, analysis of results for each block on your block diagram. So this is each individual subsystem. Now, if you notice in the mark scheme for the top band, it says 6 or more, 6 or more, 6 or more, 6 or more. So my recommendation here is that you do 7 or 8. That means that if one of your subsystems has got some slightly dodgy analysis, or the test procedure on another one's not very good, it doesn't matter. You're not going to lose any marks. So my recommendation is you do 7 or 8 to give yourself a bit of leeway for just making a little bit of an error. If you do only 6, then candidates who only do 6 generally end up in the middle band because they've made a small mistake here, a small mistake there, and unfortunately, the marker can only say that you've done it for 5 or more on this one, 4 or more on that one, and you're very easily dropping from 18 marks on your A level to, say, 10. So I would recommend you do 7 or 8. This one, the alternative subsystems, you'll notice is only 3 or more. This is basically only needed for about half of them. I would recommend that you do it for, say, 5. Again, to ensure that they can tick it and go, well, 3 or more of them are brilliant. So yeah, sure. I mean, one of them was absolute rubbish, but it doesn't matter. There was 3 good ones. The only one that is impinged by doing many is the subsystem circuit diagrams. This is, again, looking overall. So if you do 7 or 8, one of them's a bit bad, doesn't really matter. So they're looking overall. Do them on Circuit Wizard. It's easy to do them well on Circuit Wizard. So these are the sections: specification, alternate methods. There's only need for about half of them. Calculations. So this is not directly referenced on the mark scheme, but it is needed. So that's logic tables for logic circuits, or if you are looking at something that's analog, then it needs to be finding the correct resistor values or capacitor values. Notice on the mark scheme it does say including both analog and digital. And again, you'll notice here it says including both analog and digital. So you can throw away 2 marks on your A level for just not involving one bit of analog in your circuit. Most of you will have something digital. The analog can just be, if you're really desperate, can just be a pot. So it can just be a dial. It needs to be an entire separate subsystem, not a stable where you've got a variable resistor in it that you tune. That's not a separate subsystem. That's part of the A stable, which is a digital thing. So it does need to be something separate, but it could be that you have a dial going into a comparator, and when the dial goes high, it triggers something, and when it goes low, it doesn't trigger it. So that's kind of the easy way out. Obviously, thermistors or LDRs are other things that are available that are analog. You can work entirely in analog. You can use the microphones that are available, and you can do something that's related to audio systems. I would recommend that you've fully got your head around Chapter 6 audio systems if you want to go there. And I would know that it is probably really a lot more difficult than doing digital. I would thoroughly recommend that you focus on this coursework being year 1 content. That makes your life a lot easier and is almost entirely digital. So if you base it around timing circuits and sequential logic and logic from year 1, you will have a fairly easy time and throw in an op amp with a comparator, and that'll do. Circuit Excuse me. Okay, so these are all the sections. Let's look at an example because it's easier to see it. There are 4 exemplars. You're welcome to look at them. Please do. There's also a student guide. The student guide has a useful table for alternate methods because you may not think of an alternate. A lot of things we've looked at have alternates. So, for instance, the 555 A stable has a Schmidt inverter A stable as an alternate. They do the same thing. They pulse. There are many things. You could have a comparator, an alternate to that would be a Schmidt trigger. Again, they output high or low depending on the input analog value. Do have a look at the student guide for more examples. So this is one student's work. This is perfect. You'll notice it says subsystem 9. They did 9. And each section is just been ticked because it's perfect. There's no problem. So at the beginning, you should have a specification. And specification should really amount to 1 bullet point's worth of information. They've broken it down into 3 things. This first point here is pointless. They don't really need that. They can include it, doesn't matter, but it's not really needed. This is really what their specification is these bottom 2 points. And they could have easily said the subsystem must output logic 1 if all 3 inputs are logic 1, otherwise logic 0. And that would have been fine. So your subsystem should have a single function and it should be 1 bullet point on the specification. This next bit is alternate methods. They've gone a bit overboard and done 3 alternate methods. You don't need to do that. You can just have one alternate method to 4 or 5 subsystems, and you're going to get full marks. They've done 3 because they thought of 3. When you look at the alternates, make sure that you've got a circuit diagram. This is just a sketch because it makes it really clear to the person marking it what you're talking about. So sometimes, particularly with logic systems, a student will say something like, this could be approximated with NAND gates instead. And they don't really make it clear how that could be done. So NAND gates are obviously a really good alternate to any kind of logic system because you can just do combinations of them. They do take up more space because there's more gates involved. However, if you've got lots of logic, you may end up saving space because you may end up with 7 NAND gates in use instead of an OR gate and an AND gate, which would be 2 ICs, which take up more space and more money. Actually, they're both 2 ICs, but you get the kind of idea. Do make sure that you've listed advantages and disadvantages of each one. You shouldn't be considering an alternate that just is bad, and it should fulfill the function. So it should, whatever the function is, it should fulfill it, even if it's not very efficient or cheap or whatever. Notice here they've explained. You need to explain why you've picked whatever method you picked. So you've given the methods with a picture, you've given advantages and disadvantages. These are quite general, these advantages and disadvantages. This should be putting it in the context of your circuit. So for instance, for NAND gates, it may well be that yes, you could have a NAND gate chip. This will take 2 gates instead of 1, and you're not using any other logic. So there's no point. Why would you do that? That's not a gain. The spare NAND gates aren't a gain because you're not going to use them. So think about it in terms of your circuit. Calculations for logic, this should just be a truth table. For something more analog, possibly calculations of resistor values or capacitor values. Any kind of formula that you will have used to calculate the values. Test procedures should explain how you are going to test it. It should include the equipment, so voltmeter, how it's going to be measured, and then you should have the results. You don't need to have a picture of every single voltmeter output if there are many of them. You can see that this person is only given 2. That's perfectly acceptable. I'm just going to take up pages and pages of pictures of a multimeter reading exactly the same thing. So don't do that. But a couple of pictures at least should be reasonable. Now notice This analysis isn't wonderful. It's a little bit hard to see. And the results are expected. Output Q is only logic 1 if all 3 inputs are logic 1. And they should be saying meets the specification, because it does. It does meet the specification, which is here. And that's what your analysis should always be saying. Does what you got meet the spec? The last bit is circuit diagram. You can do this in Circuit Wizard. I would recommend that Circuit Wizard is a lot easier. Now, the only potential downside is that students end up with basically building the whole circuit on Circuit Wizard, and then they just crop. They just copy the whole thing and then just crop that bit of it. That's not at all acceptable. So it does need to be an entire circuit subsystem, not something like this. So let's say I had the same circuit and these were linked to something else. And this was linked to, let's say this is linked to a switch. This isn't acceptable because this isn't part of the specification. So that's not good. And that's the only thing to bear in mind. So that's it. You do need to do this many, many times for every single different subsystem and test them individually. So I would recommend that you crack on with this quickly. In terms of building the whole thing, because obviously that's in the back of your mind, it is very much a good idea to build each bit and test it as you go so that you don't have to come back and test it. So do that.